Hi, my name is Ray, and this is a merged talk slot for two papers. First is Tight Conditional Lower Bounds for Approximating Diameter in Directed Graphs by Mina and Nicole, and Settling SETH versus Approximate Sparse Directed Unweighted Diameter up to NSETH by myself. Okay, so there's a lot of words in these titles. What is this talk about? This talk is about computing the diameter of a graph. The diameter is the maximum shortest path distance between two vertices in the graph. We'll mostly be talking about computing diameter in directed graphs, and we'll be focused on approximation algorithms. So instead of returning the diameter, you only need to return, say, between half the diameter and the diameter. And we'll be talking about conditional lower bounds for approximating diameter, so hardness of approximation results based on the strong exponential time hypothesis. So you won't need to know the definition for the talk, but if you haven't seen this before, SETH states that for all epsilon, there exists a case such that k-sat needs 2 to the n times 1 minus epsilon time. So basically, you can't do much better for SAT than checking all the possible inputs. Okay. So now let's jump into it. So again, the diameter is the maximum shortest path distance between two vertices, and diameter is a very natural graph parameter, and it should go without saying that we'd like to be able to compute the diameter quickly. It's a useful measure of the complexity of a graph in real-world networks. Some of the examples are listed here. And probably the most popular example of the diameter is the 6 degrees of separation phenomenon. So that says that for any two people, you can take 6 connections to get from one person to the other. And this is some statement about the diameter of a social graph. So diameter comes up everywhere. We like to be able to compute it. And that's what we're going to be talking about in this talk. So before we jump in, it'll be helpful to orient yourselves to tell you that there's many settings of diameter. There's directed graphs, undirected graphs, weighted graphs, unweighted graphs. For every pair of adjectives, I've given you a graph and the corresponding diameter. And in this talk, we'll mostly be focused on directed graphs. And it'll be helpful to keep in mind throughout the talk that directed graphs are a generalization of undirected graphs. Every undirected graph can be made directed by replacing every edge with 2 directed edges. Similarly, all unweighted graphs are weighted graphs because you can make every edge just the edge of weight 1. So the weighted solving diameter in weighted graphs is a more general problem as well. So for these more general problems, it's harder to find algorithms and easier to prove lower bounds. So it would be helpful to keep this in mind throughout the talk. So the main question for this talk is, how fast can we compute the diameter of a graph? So if we want to exactly compute the diameter, one thing we can do is just compute the shortest path between every pair of vertices. This solves something called the all pair shortest path problem. You can do this by running Dijkstra or BFS from every vertex if your graph is unweighted. And this takes quadratic time. So we're going to list all of our runtimes in this talk in terms of the number of edges, m, of the graph. This is just the short for the size, roughly the size of the input. And of course, if your graph is dense, then you can do it in faster than m squared time. But if you want a runtime that's just in terms of the size of the input, the best we could say is quadratic time for the solves pair shortest path algorithm. Okay, so for exact algorithms, quadratic time is the best we can do. So you could ask, can we get faster algorithms with approximation? And the answer is yes. So there's a simple 2 approximation in near linear time. And the algorithm is easy to describe. So we fix some vertex v, and we compute the distance from b to every other vertex, right, running Dijkstra from b. And we return the distance from b to the furthest away vertex, which is also known as the eccentricity of b. And we're guaranteed that this distance is always between half the diameter and the diameter. The proof is short. So see this, if the diameter is d, that means there's 2 vertices a and b at distance d. And by the triangle inequality, that means that either the distance from A to V or the distance from B to B is at least d over 2. So just to give you an idea of what's coming, the main result of these works is that assuming SETH, this 2 approximation is optimal in directed graphs. So that means that in near linear time, you can't get a 2 minus epsilon approximation unless SETH is false. Okay. But before we go into that, let's keep talking about algorithms. So we're going to put our algorithms in this picture, which will come up throughout the talk. So you want to orient yourselves. On the horizontal axis, we have the approximation ratio. And on the vertical axis, we have the runtime exponent. And obviously, we want faster algorithms and better approximations. So we want algorithms that are down and to the left. So the all pairs shortest path algorithm, we can get an exact algorithm in quadratic time. That's what we saw on the previous slide. And we can also get a 2 approximation in near linear time. It's also known that you can get a 1.5 approximation in m to the 1.5 time. This is this line of 3 works. And in directed graphs, these are the best known algorithms. If we're working with undirected graphs, there's also known that you can get an almost 2 minus 2 to the minus k approximation in m to the 1 plus 1 over k plus 1 time. This almost means that you also lose an additive factor in addition to the multiplicative approximation ratio. So in generic graphs, these are the best known algorithms. More is known if you assume your graph is, say, planar or has bounded tree width or something, but for generic graphs, this is the best we know how to do. So a natural question is, are these algorithms the best possible for computing the diameter? Some questions we could ask in this direction are, can we get a faster exact algorithm? Is there an exact algorithm in truly subquadratic time? We could also ask, is there a better than 2 approximation in near linear time? Or is this simple 2 approximation from the triangle inequality optimal? We could also ask, so in directed graphs, it's not even known if you can beat a 2 approximation in better than m to the 1.5 time. So is that possible? And these last 2 questions appear in this survey called SETH versus approximation. Okay, so to answer some of these questions, we're going to use something called fine-grained complexity. So in classical complexity theory, you have these complexity classes, and you can make statements like, if P is not equal to NP, then 3 coloring cannot be solved in polynomial time. But statements like this aren't going to be good enough for what we're doing, because we're not trying to distinguish between polynomial time and not polynomial time. We're trying to distinguish between, say, linear time and quadratic time. And so that's where fine-grained complexity comes in. And with fine-grained complexity, we're going to be able to make statements like, if some hypothesis is true, then diameter cannot be solved in, say, truly subquadratic time. So some common hypotheses we assume in fine-grained complexity are SETH, 3-sum hypothesis, the all-pair shortest path hypothesis, and others. The first 3, I think, are the most common. And in this talk, we'll be dealing mostly with SETH and a little bit of NSETH. So fine-grained complexity, it's been this exciting field with a lot of applications and a lot of hardness results that have been proved. The list literally goes off the page, and if you're interested in learning more, you can refer to Virginia Williams' survey on some fine-grained questions in algorithms and complexity. Okay, so now let's talk about some of these hardness results. So we'll first look at directed weighted graphs, and then we'll move on to directed unweighted graphs. So remember, for directed graphs, these are the best known algorithms. And the first thing we could ask is there a faster exact algorithm? And it turns out the answer is no, assuming SETH. So it's known, this result shows that you can't do better than, in fact, a 1.5 approximation in subquadratic time. Okay, so that's great. That settles this question. So we could ask our next question, is there a better than 2 approximation in near linear time? Or is this simple 2 approximation by the triangle inequality optimal? So already from the previous result, we know that you can't get better a 3/2 minus epsilon approximation in near linear time. Furthermore, this was later improved to showing you can't get better than a 5/3 minus epsilon approximation in near linear time, and in fact, better than m to the 3/2 time. Later, this was improved to 7/4 minus epsilon, and we improved this all the way up to 2 minus epsilon. So both of these works show that there's no 2 minus epsilon approximation in near linear time. Okay, so this is great. So we've shown that this basic 2 approximation in near linear time using the triangle inequality is optimal, at least in directed weighted graphs, and we'll also get it for directed unweighted graphs, so for directed graphs. So there's still a little bit that's open, in particular in this white region in the picture, these approximation ratio runtime trade-offs. We still don't know if there's algorithms, or you can rule out algorithms under SETH. And so another question you can ask is there a better than 2 approximation in better than m to the 1.5 time? And what we show is that assuming a hypothesis called NSETH, I won't define it here, but it's some non-deterministic version of SETH. Assuming NSETH, deterministic SETH reductions cannot rule out such algorithms. So this takes a little bit of time to wrap your head around. So algorithms are positive results. These SETH lower bounds, these red results, are negative results. And this teal result is a negative result, a non-hardness result, or a hardness of approximation. So you can think of this result in two ways. On one hand, you can think of it as evidence for algorithms, because it's saying, under certain assumptions, there's no SETH reductions ruling out algorithms. And furthermore, this is proved by constructing two non-deterministic algorithms for diameter. And so you can see this as evidence for algorithms, and maybe this would even give a strategy to construct an algorithm by making these non-deterministic algorithms deterministic. On the other hand, if you don't believe that these algorithms exist, then what this is saying is that to prove a hardness result ruling out such algorithms, you either have to start from a hypothesis other than SETH, or you need to start from SETH but disprove NSETH along the way. So maybe a word on NSETH. Not everyone believes it's true. There's some evidence for it and some evidence against it, but it's known that if you disprove NSETH, then you prove new circuit lower bounds. So at least NSETH represents a barrier. This represents a barrier to known techniques. So that's all our results for directed weighted graphs. Now let's turn to the results for directed unweighted graphs. Again, there's no exact algorithm in truly subquadratic time, and in fact, its lower bound even holds for undirected graphs. In terms of lower bounds for near linear time algorithms, for the weighted graphs, previously the best approximation hardness was 7/4 minus epsilon. For unweighted graphs, it was only 5/3 minus epsilon. And but for our algorithms, for our hardness results, we're still able to show that the 2 minus epsilon approximation needs superlinear time. So it's the same results. And the non-hardness or an NSETH-based hardness of approximation result from the previous slide still holds. But you could ask for the remaining approximation ratio and runtime trade-offs, can we say anything? We don't know algorithms, we don't know hardness results. And what we show is we fill in the remaining white region in the picture. So assuming NSETH, a SETH reduction rules out an algorithm if and only if this inequality holds. So basically what this is saying is that our SETH hardness results are the best possible in both the runtime and the approximation ratio. And again, you can view this result in two ways. Either it's evidence for algorithms in the teal setting, or it's saying that you need new techniques or alternative hardness assumptions to prove better lower bounds. Okay, so again, let's recap our results before moving to the proofs. So our main result is that assuming SETH, there's no better than 2 approximation in near linear time for diameter and directed graphs. So the 2 approximation, the simple 2 approximation from the triangle inequality is optimal. And then there's these non-hardness results based on NSETH that say that in certain settings, SETH reductions can't rule out algorithms. So at this point, you're probably wondering what happens for undirected graphs. We prove these nice lower bounds for directed graphs, but what about computing the diameter undirected graphs? And here, the best hardness result that we have is a 5/3 hardness for near linear time algorithms. Although just this year, this was improved to a 7/4 minus epsilon hardness. And I'll also mention that all of the NSETH-based non-reducibility results also transferred to the undirected case. Okay, so in the remainder of the talk, I'll give you some of the ideas behind our SETH hardness proof. Okay, so to prove our hardness result, we're going to use something called the orthogonal vectors hypothesis. So the KOV problem, think of K as a constant like 2 or 3, says that we're given a set A of size n of n vectors of dimension d. Think of d as log n. We want to determine if there exists k vectors from A that are mutually orthogonal, which means that in every coordinate, the product of the vectors in those coordinates is 0, or equivalently, in every coordinate, one of the vectors is 0. So one way to solve this problem is you just do a brute force search over all possible k tuples of the vectors, and this takes n to the k time. And the k orthogonal vectors hypothesis says that this is basically the best you could do. A classic result says that SETH implies the k orthogonal vectors hypothesis for any fixed k. So this is really useful for us because now it says that if we want to prove a hardness result based on SETH, it's enough just to prove a hardness result based on the orthogonal vectors hypothesis. And this is how a lot of the SETH hardness results in the fine-grained complexity literature go. So that's exactly what we're going to do. So to warm up to our result, I'm going to show you first this first lower bound for diameter that says that under SETH, there's no truly subquadratic exact algorithm, or in fact, no truly subquadratic 1.49 approximation. So to prove this, we're going to turn a size n two orthogonal vectors instance. So that's, we're trying to determine if there's two orthogonal vectors, into a size m, which is roughly n diameter instance, such that if the two orthogonal vectors has a solution, the diameter is 3, we call this the yes case. And if there's no solution, the diameter is 2, we call this the no case. Okay, so why is this enough? Well, by the previous slide, SETH implies that two orthogonal vectors, this problem needs quadratic time and squared time. But then by the reduction, this means that distinguishing between diameter 3 and diameter 2 also needs quadratic time. And that implies that a 1.49 approximation also needs quadratic time, which is what we want to show. Okay, so now all that remains to do is to construct this graph, this diameter instance from this orthogonal vectors instance. So how do we do it? We start with our OV instance A, or the set A of n vectors of dimension d, which we think of as log n. And the first thing we do is we create a clique where you have one vertex for every coordinate, so every element of 1 to d. And then you also have one vertex for every vector in A. So you have n of these vertices. And for each of these vertices, you connect it to all the coordinates where you have a 1. And you do this for all the vertices, and these are all your edges. So why does this have the desired guarantee? Well, first, let's look at the second guarantee that the diameter is 2 in the no case. First, you can easily check that in either case, all of the vertices on top, the coordinate vertices have distance 2 to everything always. And in the no case, we just need to check that the distance between any two vector vertices is 2. And in the no case, that means every two vectors are orthogonal, which means every two vectors have a 1 in common in some coordinate, which gives a length 2 path through that coordinate vertex. So indeed, we have the diameter is 2 in the no case. And in the yes case, we have two vectors that are orthogonal, which means these are two vectors that don't share a 1 in any coordinate. So they don't have any common neighbor in the coordinate vertices of this graph. So that means the distance must be at least 3. Okay, so that's great. So that shows this hardness of a better than 3/2 approximation. How do we improve the hardness of approximation ratio? So what is done in this other paper, BRSVW, so they show a hardness of a 5/3 minus epsilon approximation. And now instead of starting from a 2 orthogonal vectors instance, they start from a 3 OV instance, and they turn it into a size n squared diameter instance. And they get this gap of if there's a solution, the diameter is 5. If there's no solution, the diameter is 3. And then you plug it in through the machinery. SETH implies that 3 OV needs cubic time. So distinguishing between 5 versus 3 diameter needs big N to the 3rd time, or M to the 3/2 time, because M is quadratic. And then this gives you your hardness of approximation. So here, all we've done is change some numbers around, and obviously the hard part is not changing the numbers around, but actually constructing the graph. I'll say a little bit more about this particular graph construction later, but for now, let's just keep changing the numbers. So to get a 7/4 minus epsilon approximation, you instead reduce from 4 OV and make a size n cubed diameter instance and get this gap of 7 versus 4, and this gives you what you want. And you've probably are finding a pattern by now. So what we do is we complete the pattern. So we start with a size n KOV instance and turn it into an n to the k minus 1 diameter instance, and we get this gap of 2k minus 1 versus k. And that gives us the desired result. So obviously the hard part again is not just changing these numbers and following the pattern, but actually constructing the graph, and that's the hard part of both of these proofs. And these two works use 2 different proofs, and I'll talk about one of them. So to illustrate the construction, let's look at the case for k equals 5. So here we want to turn a 5 OV instance into a size n cubed diameter instance with this gap of 9 versus 5. So to start, we'll show a slightly different construction where we'll turn our 5 OV instance into a diameter instance where the ST diameter has this gap of 5 versus 13. So the ST diameter we'll define as follows. So we'll show you by example. So they construct this graph. This is in the BRSVW paper with two sets, S and T of vertices, and they also have some other vertices. And this has the property that the ST diameter is the maximum distance between some vertex in S and some vertex in T. So if there is a solution, that means there's some vertex in S and some vertex in T at distance 13. And if there's no solution, then every vertex in S is distance 5 from every vertex in T. Okay, so how do they construct such a graph? So the set S is going to have one vertex for every 4 tuple of vectors, A, B, C, D, and T is going to do the same. All of these internal vertices, internal layers, these 4 internal layers are going to have one vertex for every 3 vectors and every 4 coordinates. So it's going to have coordinates in addition to vectors. And there's going to be an edge from some vertex in S to the first layer if the first 3 vectors are the same and there's ones in particular coordinates. So A has to have a 1 in all of W, X, Y, and Z. B has to have a 1 in W, X, and Y, and it doesn't matter what's in Z, and so on. And we do the same thing for T. For edges between the internal layers, we need the coordinates to be the same, but also you're allowed to change a particular vector when you go between the layers. So from the first to the second layer, you can change the last coordinate. From the second to the third layer, you can change the middle coordinate. And from the third to the last, you can change the first coordinate, or the first vector. Okay, so already we can see the second guarantee that the ST diameter is 5 in the no case. And why is this? Well, in the no case, any 5 vectors are orthogonal. So for an arbitrary vertex in S and an arbitrary vertex in T, we can find some W, X, Y, and Z such that this table holds. So W is going to be the coordinate where A, B, C, D, and D prime are 1, and so on for X, Y, and Z. And this gives us that we have 1s in the following places, which means that the first edge from S exists and the last edge from T exists, and then you can change the vectors as we have shown here. And this works for any S and T, so we get that the ST diameter is 5, and with some more work, we can show that the ST diameter is 13 in the S case. Okay, so at this point, we don't have a construction for diameter yet, because, for example, even though from S to T is distance 5, between 2 vertices in S, they could be a distance more than 5. Additionally, all of these internal vertices could also be distance more than 5 to other vertices. So one way around this, which is what BRSVW does, is that they add more vertices and more edges and some cliques somewhere and some other things to somehow reduce the diameter in the no case while keeping the diameter somewhat large in the yes case. And this gives them up to a 5/3 minus epsilon hardness. So for us to get all the way up to 9/5 in the k equals 5 case, and in general up to 2, we sort of add edges and vertices in a different way. So the first thing we're going to do is we're going to direct all the edges from S towards T. So as shown here. And at first this seems to hurt us because before we had distance 5 from S to T and also 5 from T to S, but now it's only going one way. But we'll also add these weight 0 edges from S to T where they connect 2 vertices that are identified by the same 4 tuple of vectors. And we'll so in practice, what we'll do is we'll actually contract them, but you can just think of them as edges of weight 0. And this is also just, so there's a nice picture. So now we not only have distance from S to T is 5, but actually from anything in S union T to anything else in S union T is 5, because say to go from S to S, you go to T and then you take the weight 0 edge back. So now all we need to do is make sure that the internal vertices are distance 5 to every other vertex. And to do this, we add these coordinate change vectors, which go from the last layer to all the other layers, including the last layer, and you're allowed to change the coordinates. All right, you're allowed to change the coordinates subject to some constraints that I'm not hiding here. And turns out if you do this carefully, then you can guarantee that in the no case, the diameter is indeed 5, and also you ensure that in the yes case, the diameter is still 9. And that's all I'll say about the construction, but if you want to learn more, you can read the paper. Okay, so that's all I have to say, and thanks for your time.